Thermodynamics. Thermodynamics. Specific heats of gas. Specific heats of a gas. Gases have two kinds of specific heats. Gases have two kinds of specific heats. They are Cp and Cv. Cp is specific heat at constant pressure. Cp is specific heat at constant pressure and Cv is specific heat at constant volume. Cv is specific heat at constant volume. Cp can be defined for unit mass and for 1 mole. Cp can be defined in two ways. It can be defined for unit mass or it can be defined for 1 mole of a gas. Similarly, Cv can also be defined in two ways, for unit mass and for 1 mole of a gas. Definition of Cp. Definition of Cp. Cp is the quantity of heat required, the quantity of heat required for 1 mole of a gas, for 1 mole of a gas to raise its temperature by unity, to raise its temperature by unity at constant pressure, at constant pressure. This will be represented by capital Cp. And small cp is defined as, the quantity of heat required for unit mass, the quantity of heat required for unit mass to raise its temperature by unity, to raise its temperature by unity at constant pressure, at constant pressure. Capital Cp is equal to capital M into small cp. Capital Cp is equal to small cp into capital M, where capital M is molecular weight. Capital M is molecular weight. Molar specific heat. Molar specific heat. The heat required to raise the temperature of 1 mole of a gas by 1 degree. The heat required to raise the temperature of 1 mole of a gas by 1 degree. We can define Cp or Cv like this. If it is at constant pressure, then it will be Cp. If it is at constant volume, it is Cv. The unit of molar specific heat is joule per mole per Kelvin. Joule per mole per Kelvin. If dq is the heat given for n moles of a gas, for n gram moles of a gas, if dq is the heat given for n gram moles of a gas and the rise in temperature is say dT, and the rise in temperature is say dt, then molar specific heat C is given by, molar specific heat C is given by 1 by n into dq by dt, 1 by n into dq by dt. If it is at constant pressure, then it becomes a Cp. If it is at constant volume, then it becomes Cv. Definition of Cv. Cv is quantity of heat required for 1 mole of a gas to raise its temperature by unity at constant volume. Cv is quantity of heat required for 1 mole of a gas to raise its temperature by unity at constant volume. And small cv is the quantity of heat required for unit mass to raise its temperature by unity at constant volume. Capital Cv is equal to capital M into small cv, where capital M is molecular weight. Relation between Cp and Cv. Relation between capital Cp and capital Cv. At constant volume, the energy is used in increasing the internal energy. At constant volume, the energy given to a system is used in increasing the internal energy. At constant pressure, the energy is used in increasing the internal energy, and in doing external work, So, Cp is greater than Cv. Cp by Cv is equal to gamma. Cp by Cv is equal to gamma, the ratio of specific heats. Gamma is the ratio of specific heats. External work done by an ideal gas. External work done by an ideal gas. If gas is enclosed by a piston in a cylindrical vessel, with a piston, tight and smooth piston. Suppose capital A is the area of the piston, the area of cross section of the cylindrical vessel as well as that of the piston is capital A, and by applying a pressure P, if the gas is compressed by a distance, if the piston is moved by a distance dx, then the gas will also do an amount of work equal to P into dV, where P is pressure and dV is the increase in volume. P into dV gives the work done either on the gas or by the gas. The work done on the gas or by the gas is given by W is equal to P into dV. External work done by a gas. The relation P dV can be derived as follows. The pressure of the gas is say P and the area of cross section of the cylindrical vessel or the piston is say capital A. Then the force applied by the piston is Pa. The force applied is pressure into area P into A. The distance moved by the piston is dx. So work done is equal to force into displacement. Pa into dx. But A dx is dV, the change in volume. So work done becomes equal to P dV. To evaluate the value of P dV, that is work done by the gas. Work done by the gas is given by P dV. If work is done at constant pressure, say if P is the constant pressure and the volume changes from V1 to V2 as shown by the graph AB. AB indicates the work is done at constant pressure and the volume increases from V1 to V2. So work done is equal to P into dV, but dV is V2 minus V1, hence W is equal to P into V2 minus V1. This is the work done at constant pressure. This is the relation for obtaining the work done at constant pressure. Evaluation of P dV when pressure is not constant. In the first figure we have seen that the pressure is constant and work done is P into V2 minus V1. In the second graph we notice that the pressure varies. The pressure at A is more and the pressure at B is less, and the pressure is changing and the volumes will change say from V1 to V2. At A the volume is V1, the volume at B is V2. Then when the pressure is varying, the work done will be calculated using the integral P dV between the volumes V1 and V2. So W is equal to integral P dV under the limits V1 and V2. Like this we evaluate this integral to obtain the work done whenever the pressure is not constant, when the pressure is varying. Derivation of the relation Cp minus Cv is equal to R. Consider 1 mole of an ideal gas of volume V and pressure P at temperature T. Consider 1 mole of an ideal gas of volume V at pressure P and temperature T. This gas is enclosed by a piston of area A in a cylindrical vessel whose cross section is also equal to A. The gas is enclosed by a smooth tight piston of area A in a cylindrical vessel. Derivation of the relation Cp minus Cv is equal to R. By giving dq heat energy, if the gas is heated at constant volume, and the rise in temperature is dT, then the heat given dq is given by dq is equal to 1 into Cv into dt. 1 is number of moles. Since we have considered only 1 mole of a gas, Cv is specific heat at constant volume, and dt is rise in temperature. So, this is nothing but increase in internal energy. By giving dq prime heat energy, if the gas is heated at constant pressure, and thereby the rise in temperature is dT, then the heat given dq prime is given by, dq prime is equal to 1 into Cp into dt. 1 is number of moles, Cp is specific heat at constant pressure, and dt is rise in temperature. Like this, we calculate the heat given at constant pressure and the increase in internal energy. When heated under constant pressure, a part of the energy is utilized in increasing the internal energy, and another part is utilized in doing external work. Internal energy part is dq and external energy is dw. External work done is dw. The part utilized as internal energy is dq and the external work done is dw. Since rise in temperature is same in both the cases, that is at constant pressure and constant volume, we get dq prime is equal to dq plus dw. dq prime is equal to dq plus dw. Work done dw. The pressure of the gas is P and the area of the piston is A. So, force applied by the piston is Pa. Distance moved by the piston is dx. So, work done dw is equal to force into displacement. dw is equal to Pa into dx, that is equal to Pdv. Since area into dx, displacement, is equal to dv, change in volume. By substituting the values of dq, dq prime and dw in the relation dq prime is equal to dq plus dw, we get Cp into dt is equal to Cv into dt plus Pdv. Cp into dt is equal to Cv into dt plus Pdv. From ideal gas equation, Pv is equal to RT. Since we have taken 1 mole of a gas, the ideal gas equation is Pv is equal to RT. By differentiating, we get Pdv is equal to RdT. Hence, the above relation becomes Cp dt is equal to Cv dt plus RdT. Or Cp minus Cv into dt is equal to R into dt. dt gets cancelled. So, we get the relation Cp minus Cv is equal to R.